now that we know the basics of Unity, we can actually start playing around with Unity here. So we're actually going to do some coding this video, but before that, I just want to explain a little bit more about how Unity works. So first of all, Unity is a component-based game engine, and this means that everything in the engine they are components. So for example, the camera here is a component, the flare layer is a component, the audio listener is a component, transformer is a component. You get the deal. So what this means is that when you're working with Unity, you have to be you can't think purely how you would do it in C#. For example, in C# you will instantiate new scripts with a new keyword. That is not always possible with Unity. So I'm going to show you an example. So first of all, you just make a new class and just call it arrow, and not in the scenes folder, in the assets folder. And also make a new folder called scripts. Put your arrow class into there. Save your scene as scene 0 in the scenes folder. And there you go. Now you have an arrow class. So what you do next is you create a game object, call it arrow, and put the arrow on it. Okay, and just make sure that these are 0. It's nicer. So if I go into this script now, whenever this guy wants to work, okay, there we go. Sorry. So if we go into this class now, this Monobehaviour here is a Unity class. So Monobehaviour is the core class that anything you make will derive from. So anything that is a Monobehaviour cannot be instantiated with a new keyword. They have to be added as components. So for example, this arrow component on this arrow game object here. So that means that if you wanted to do, you can't do that. It doesn't work. You have to use .add component. So if you wanted to add dynamically in code this arrow object onto your game object, you would basically do game object, which is a reference to the game object we're currently on, the script, the game object the script is attached to. You would do add component, and then you would do arrow. And that's the correct way of adding a new component. Now the same thing applies for getting a component. So if you wanted to get this arrow script, like we're in the arrow script, so you wouldn't have to do it, but technically you will have to do get component and then arrow, and then you will have your arrow script. Okay, so there's add component and get component for accessing those interfaces. So next thing, oops. So what we're gonna do now with this is we're gonna make this arrow move on the screen. So first thing I'm gonna do is I have a sprite, so I'm gonna make a new folder here called sprites, and I'm just going to go ahead and add a little sprite I made to that. There we go, arrow. So that's my little arrow sprite. You can do whatever you want for the graphic. So first you do is just delete this one and then go to this add here. So game object, 2D object, and sprite, and name that arrow again, and just initialize it at 0, and just drag and drop this arrow sprite onto the thing. So you can see this is quite big. There's a couple of ways you can get around it. One of them is to change the scale. For example, this would be half the scale. The other way is to change the pixels per unit. So this one is 395 by 395 pixels, but the pixels per unit is set to 100. So if I wanted one movement, so one unit, to be the entire width of this guy, I would have to set this to 395. That means that this guy is now 1 unit large. So if I move it, if I make a new arrow, Control C, Control V, and I move it 1, That's actually the entire width of the object, because that's how long a unit is, because I set it here. All right, so I'm just going to work with that as 395 for now. So here we're in our scene view. Some hotkeys: you can press F to focus on an object, like this. You can scroll out and scroll in with your mouse wheel. You can click down the middle mouse button to move around your scene and all that. Yeah, so next thing you do is select your arrow object, go to your script folder and put the arrow script on, and you save your scene. So we're gonna make this guy move over there, and then eventually we're gonna make him move back again. Just to play around with the transform component here, which we're gonna be exploring. So first thing you do, open your arrow script, and what I like to do is to just make it explicit that these are private, because they are. Like this. And then what we're gonna do is we're gonna add a public vector2 start position. That's where it's gonna start moving from. We're gonna add a public vector2 end position. So now what I'm about to show you is one of the neat functionalities of the Unity editor here. So since we have these public vector2 start positions here, if you go out to your Unity editor and you wait for this thing to load your changes, when you click your arrow object again, you're going to see that you're able to actually set these in the inspector here. This is very powerful and saves you a lot of coding work. So for now, I'm just going to do this manually and just go, okay, I want this guy to start at -6 and I want him to go to 6. Okay, so then I just go -6 there and then 6 for the end position on the x-axis. Okay, so next thing we'll do here is in the start method, we don't actually have a reference to our transform yet. So our transform is our controller for moving this guy around in world or local space. So there's a couple of ways you could do this. So one of them is that the game object that is attached to this guy actually has the transform thing conveniently accessible for you. You can also do just transform as well, like that. But it is better practice to not use those and instead define them and cache them. So define your transform up there. So I have an underscore here, and then just do transform equals get component transform. So that's going to get that transform component and cache it in this variable in our start method. Okay, I actually didn't walk through what these methods do either, so let's do that. So first of all, Monobehaviour is a special class that all game objects in your scene derive from. They cannot be instantiated with a new keyword, and they have a couple of method hooks. So start is one of them. The start method is only called once in the object's lifetime. So the moment the script has been initialized, the start method will be called. The next one, which is one of the most important ones. These are the two most important ones here. This is the update method. So this one will always be called every frame. Okay, so if you're running your game at 800 frames per second, this update method will get called 800 times per second. There's one more thing here that is important to realize and know, is that the start method, all start methods in your scene will always be called before any update methods get called. This is important because you might have to do some initialization logic in here and then use it in the update method, and then if it hasn't been declared, then your stuff is going to break because of the null reference exception. So you don't have to worry about that if you are getting your variables in the start method. Okay? Okay, so once we've done that, we're going to do some more stuff here. First of all, we're going to take our transform component, and I'm just going to really drill this in here. You see these variables on the transform component here? There's position, rotation, and scale. All of these guys can be accessed from the transform. So if I do transform dot position, it's there. I can do transform dot rotation, it's there, and I can do scale. Actually, scale is called local scale, but they're all there. Okay. The only difference between something like transform and position and local position is if your object is nested into another object. We don't have to worry about that quite yet, but for now just do transform.position equals start position. So that means that the moment this game scene loads, our object, our arrow here, is going to be set at the position we defined here, so -6 x and y 0. So when I click start, you're gonna see that this guy is positioned at -6 0 0, just like we defined in code. Great. Okay, so the next thing I'm going to do now is I'm going to make this guy move. So there's a couple of ways of doing this, and I'm going to show you two ways. One of them is by translating your transform, and one of them is by linearly interpolating over time. And they are both useful, and it's up to you how you use them. Generally, transform to translate is very useful for example, when you're moving things with input, while lerp is very useful for something that's always going to move in a very predictable manner. Okay, so I'm going to define a new method called movelerp. Move translate, and I'm going to start doing some maths here. Okay, so the first thing we need to do is we need to know the distance between our start and end position. So I'm going to define a new variable, which is going to be float travel distance. And I'm going to use one of the vector2 helper functions, vector2.distance, which gets the distance between two points. So I know a lot of these are not familiar to you. You're going to be using them a lot. You'll learn them over time. I recommend that you at least learn some vector mathematics. In my case, when I started learning Unity, I didn't really know any vector mathematics. I just kind of painfully learned it over time. But yeah, however you want to do it. If you already know vector mathematics, great. If you don't, just try to understand that this actually just gets the distance between your 2 points. It's not that complicated. Okay, so now that we have the travel distance here, we can start fleshing out our method here. Yeah, so the first thing I'm going to do is I'm going to start defining this move vector. So var is just it's basically vector2 move. So end position. Oh, sorry. Equals end position minus start position dot normalized. So doing this, this is just a simple formula for getting the direction towards a point. So now we're getting the direction we need to move to go from start position to end position. And the reason why I'm doing normalize here is because I don't want this vector to have a length. I just want it to be 1 0 or -1 0. I don't want it to be something like 5.5, 0. I just want it to be a direction with no length. Okay, so now that we have the move direction, we need to actually calculate the speed at which we should travel. And that's going to be, the speed is going to be the distance that we need to move divided by distance duration that we don't have yet. And that's going to be the speed at which we travel at. So I'm going to define yet another variable here called distance duration. And that's basically just how long in seconds is it going to take for us to move from point A to point B. Okay, so we're going to initialize that in the editor soon. So our travel distance divided by the distance duration, that is our speed. So that one of the simple ways of doing this is doing transform.position equals cast the vector this plus move times speed. That's going to move our position. So the reason why we need to cast this to a vector2 is because this transform.position is technically a vector3, while we have declared our move direction as a vector2. That's why. Okay, I'm just going to make this bar because I like that better. Okay, so when we play this, you're going to notice something strange. You would assume that, okay, so we're going to say that this is going to take 5 seconds. You're going to notice something strange. That's very strange. Oh yes, should actually need to call our method as well. So now we're going to call this method every frame so that we can move towards our point. So if I go here, you're going to notice that the arrow just disappears off screen and it goes very, very fast, right? And you might be wondering, what's going on? Why is it leaving the scene? That's very fast. What have we done wrong? So the explanation is very simple. I defined that this would take X amount of seconds, but we're calling this at our frame rate. So this is actually locked to our frame rate. The speed is locked to our frame rate. That's something you need to avoid. Okay, it's a very common problem. People make this mistake all the time. What you need to do is you need to know how long it takes for one frame of yours to complete so that you can know your frame rate, or else your speed will be frame locked. There's a very simple way of doing this in Unity. It's just doing multiplier speed. We can do it actually here. Multiplier speed by time.delta time. So time.delta time is simply the time in seconds it took to complete the last frame. So that means that even if you're running this at 800 frames per second, 400 frames per second, 60, 30, it doesn't matter. It's always going to move at the same speed. So this is always important when you're using something in the update function and you want it to be a constant thing, not a thing that is locked to your frame rate. So if we play this again now, you're gonna notice that we have fixed our problem. It's moving at the speed that we want, and in 5 seconds it will be at our our 6th position there. But it still keeps going off the screen because we haven't told it that it shouldn't do that. So to fix that, I'm just going to do something simple for now. I'm going to define a nullable float called start time. So a nullable float is simply a float data type that can be null. If I just did float, I can't declare this as null because it's not nullable. So I'm going to use the nullable version of this. Okay, and then in our update call, I'm just going to check if the start time is null. I'm just going to do start times equal time.time, which is simply the time at the beginning of this frame, the time in seconds since the start of the game. Okay, so now that we have that guy, what I'm going to do is I'm also going to get the current time, which is time.time. And for now, I'm just going to do if, so time passed. So that's the time passed, right, in seconds. So if time passed is greater than or equal to the distance duration, for now, we're just going to return. So if I play this again now, you're going to see that this guy is moving, and when it reaches 6, it'll stop, just like we expected. So that's all nice. Now we have an arrow that moves from -6 to 6. It's nothing exciting, but it teaches a valuable lesson with how to work with this stuff. There's one more thing here, is that I said that we will be using something called translate. Actually, for now, I just did this the very simple way of just setting my position equal to this position plus the move direction and the speed. Instead of this, it's better practice to use a method called transform.translate. And the reason why transform.translate is nicer is 1, you don't have to write as much code, and 2, you can choose what you're moving in relation to. So whether it's world space, local space, or another object. So it's just a nicer way of moving your objects. So what we do here is just move direction times speed instead of this guy. So less code, and it's more flexible. So this is going to have the exact same result when we play it again. It's just going to move from -6 to 6, just like we expect. Okay. The next way of moving is by something called linear interpolation, also just called lerp. So what you need to do then is lerping is very simple. It basically goes, you have a start, so let's do start equals 0 and equals 10, and then a lerp factor. So when lerp is 0, the position would be 0, and when lerp is 1, then the position would be 10. And that's all it does. It just goes from 0 to 1 and goes and interpolates that to these values. So 0.5, a lerp of 0.5 would then be position 5. Okay. So knowing that, we can start programming this. So I'm gonna do var time passed equals time.time minus start time dot value. So that's the start time we set. Our lerp is going to be the time passed divided by the distance duration. So that means that the moment time passed is equal to our distance duration. So for example, in our case, 5 seconds, lerp will be 1. And then, so that means that at 1, we are at our maximum position. So then I will set my move lerp equal to vector2.lerp. That's the function. Start position, end position, and our lerp. And then simply do transform.position equals move lerp. So you're gonna notice a couple of things here. One, you don't have to use time.delta time because this value is not fixed to the frame. This is simply time in seconds since you called it last time. So time passed keeps incrementing as you would assume. It's just real time seconds. So if I'm just replacing this method now with our move lerp, that's going to work in the exact same way. It's just a different way of writing the same kind of code, and they have different use cases. And also the lerp is a little bit more accurate. All right, so now that we have these two methods, we're gonna look a little bit more at on the component-based system here. So you can see that there's another component here called Sprite Renderer. So currently we have done get component transform. There's also a Sprite Renderer here. We can also get that one by simply doing defining it like this: private Sprite renderer, and then just like with the transform, we'll use to renderer equals get component sprite renderer, which is the name of this component right here. So what we're gonna do is we're gonna make this arrow move over here. We're gonna make it flip like this and then move back, flip like this, and just keep going back and forth forever. So how do we do that? It's quite simple. First of all of these variables I mentioned before can be accessed through code. So for example, this flip variable can be accessed as well. So knowing that, we're gonna write a method to flip our sprite, like a toggle method. So we're gonna write a private void flip sprite, and then just do the renderer that we set previously. We're just gonna do dot flip x equals not renderer to flip x. So that means simply that we're setting it true, false, true, false, true, false. We just keep flipping it, okay? The next thing we're gonna do is we're gonna flip our movement direction. So how do we do that? There's many ways. The simplest way is to simply swap our waypoints whenever we have reached one, right? So the moment we arrive at the end position, we set the end position equal to the start position, and the start position will be the end position. So we're simply going to do a var temp equals start position equals end position, and our end position equals temp. Okay. So now, instead of just returning whenever time passed is greater or equal to the distance duration, we will do flip sprite, flip movement direction. So that means that when time passed is greater than this, we'll flip our sprite and we'll flip our movement direction, and we'll keep looping in a ping pong fashion. There's one more thing that we need to remember to do here, is that we have set our start time now, and the moment this has happened, it will never happen again, because time passed is always going to be greater than this, because we're not resetting our start time. So there's one more thing we need to do, and that is to say that start time is equal to time.time to reset it to our new start point. So now that we've done that, and it doesn't matter which one of these you're using, they work the same way. So now that's done, if you play your scene again, you will see that the moment this guy reaches 6, flip X is toggled, it turns around, and it goes back to the start point, and it flips again, and it keeps doing that forever and ever. It's quite simple, and just to prove it to you that these ones are the same, I'll comment this one out and just play it again. Voila. So nothing super exciting, but it teaches a couple of valuable lessons here. So to summarize, one, you can get components and add components. So you can get a transform component on your object and use all the variables defined here and more. There's more variables than the ones you see here. The same with the Sprite Renderer, the same with any other kind of component that is attached to your object. Additionally, there's some other things there we haven't explored yet, but these guys can also be accessed from your game object. It will simply be gameObject.tag or gameObject.layer, or for example, gameObject.aesthetic. So it's quite useful and intuitive. What this also means, I'll show one more thing here, is that since Unity is component based and everything is pretty much a template, this is like a recipe for an arrow now. So what I usually do is I create a prefabs folder, so that's where we keep our building blocks of our games, and I'll drag our arrow in. Okay, so now we have this guy saved here. Now I'll show you the power of Unity here. We're gonna drag out a couple of these guys into our scene. And what's interesting about this is that, yeah, so first of all, I'm going to set this guy here, approximately like this, to show you what Unity can do. Okay, so we're gonna take this guy and we're gonna set him at 4, this one at 2, 2, 0, 0, -2, -2, -4, -4. And this one we can just get rid of. Cool. So now when I play this, now we have a bunch of arrows on the screen. So what's good about this is that while these are copies of each other in a way, they are simply a recipe. So you can edit all of these guys individually. So for example, we can edit the distance duration. So this guy is going to start moving a lot faster. We can take this guy. We can make this guy move even faster. Oh, he left the screen. That's okay, he can leave. I don't care about him anyway. So you can see how this can be very, very useful when you're making a game. You can also make them move at different locations like this, and yeah. So just play around with this, get familiar with the transform component and movement in general. These are the main methods of movement, but once you start working with physics objects, it's a little bit different. We'll be exploring that in a different video, but for now, I hope you've learned something, and thank you for watching.